Okay, so in this presentation, I'm going to go over some review from previous lessons regarding heat loss and gain, and U values and R values and so forth, and then also get into a little more detail about heat loss and gain to help prepare you for the lab this week. So, as I said, a lot of this will be a review, and during those parts I'll go over pretty quickly. So we'll start. First of all, the difference between heat and energy. There was a video that's posted from Bill Nye. They did a good explanation of this as well. But remember the second law of thermodynamics. Heat always will flow from areas of higher to lower temperature. It's just the law of physics. The only way you can make heat go the other direction is by adding heat to the system. So for our purposes, heat will always flow from higher to lower temperature. This is really important, in particular, when you're looking at heat flowing through a building surface, so like a attic space or a wall or whatever, it's always going to go from the warmer side to the colder side. These numbers are approximations, but if you look at sort of the average winter heat loss, a lot of it's lost through the ceiling. It should make sense. The warm air rises up, and then it sort of pushes up against the top, and then it's going to work its way through. So you got to be really careful here. This is heat loss, not air loss. Okay, so heat loss through the ceiling, heat loss through the windows, heat loss through the walls and floor, and then the air loss is here, this 15 to 25% in air leaks, which we'll address at a later time. That just gives you kind of an estimate. So there are other ramifications for heat loss other than having to pay extra money to provide extra heating and use your heating system more often. So here's one really good example of this. If you ever go around a neighborhood in the winter time and there's snow on the roofs and you see some bare spots, so like some pretty prominent, like not just a little tiny bare spot, but like a real bare spot on the roof that's where the snow is melted, that's very often a sign that there's heat that's escaping through like the insulation in the attic, and then that gets up to the attic, to the roof, and it heats the roof and it melts the snow. Now it's possible that there's a dark, there could be like a stick that fell down on top of the snow that's dark and absorbs the sunlight, and there's other ways that this can happen. But very frequently, if you see like a big bare spot, that's often a sign that that's actually heat coming up through the unconditioned attic space. So, okay, so what's the big deal? Well, the problem is when that snow melts, it turns into liquid water, of course, and it runs down, and if you see icicles like this, they may be nice to look at, very picturesque, right? Everybody likes to see the icicles on the gutters. That's a sign that your snow is melting, which means you're losing some heat. And the problem is when the gutter, when that freezes, that creates what's called an ice dam. And then when the other snow melts, it should run down in the gutter and run away from the house. But if you have solid ice in the gutter, it's going to be one of the last things to melt, and so it creates a little dam in the gutter, and you can actually have water, liquid water, build up in the gutter. And as we all know, water is really damaging to houses. So that can cause some rot and so forth. So if there are icicles, that's a sign of an issue that you should take care of. In terms of the summer heat gain, so in the winter, you're trying to prevent heat from moving out into the colder air, and in the summer it's the opposite, right? So you're trying to prevent the heat from coming in. Okay, and so that same insulation that prevents heat loss in the winter also helps prevent heat gain in the summer. And if you've ever been up in a hot attic in the middle of the summer, like they can get really, really hot. And so that, if you think about the difference in temperature between that attic space and the conditioned space below, the bigger that temperature difference is, the more that heat's going to want to travel into the conditioned space, right? So you want to prevent that from happening. One way that you can help sort of mitigate that problem is by having things like a gable vent right at the top, or sorry, the gable vents at the end, and then you can have the ridge vent at the top. Okay, and so what that does, that can help sort of draw some of that heat out, so you don't have that as big of a delta T between the attic space and the living space. There are other ways that Buildings gain heat. We've talked about solar heat gain. Occupant and other internal loads are really, really important, especially for commercial buildings. So people emit heat all the time. We're metabolizing things, and we're emitting some heat. You look at the average adult; it's around 250 BTUs per hour. If you're exercising or doing some other kind of high intensity activity, you'll increase your heat loss. I think that's pretty intuitive, and this can add up. So especially in a commercial building, you think about Delaware Tech on a normal day, pre or post COVID, that is 1,000 people in the building. They're all emitting a whole bunch of heat, right? Add to that the fact that any electronic equipment, all of that electricity, almost all that electricity ends up as heat. So lights, TVs, motors, you name it, computers, printers, doesn't matter. Anything that uses electricity in the building, it really ends up as heat. And so that can be actually really significant in terms of the internal load, to the point that some commercial buildings, this is actually pretty common in like a college building like Delaware Tech, that in the middle of the winter, if it's full, or it's being fully utilized, there's so much internal heat that you may only need to heat that building really to like 45 or 50 degrees inside, and then all of the internal loads will take it up to the appropriate temperature from there. So that's something called a balance point temperature, which we won't really get into too much. But just so you know, those internal heat loads can be very, very significant, especially in a commercial building. Industrial building as well. Think of like a big factory that has all kinds of huge mechanical equipment that's operating all the time. Like, that's a significant internal load. That's heat that will end up heating the building. So in the summer, you can imagine that's a problem, right? I mean, you have to make up for that extra heat. In the winter, it's actually a good thing, because you can keep the building warmer without providing as much heat. And so just so you know, that's the internal heat loads are really important. And if you have, just as a quick example, if you have 1 kilowatt, right? So if you have 1,000 watts of lights in a room, if you have them on for 1 hour, right? So you have 1,000 watts times 1 hour, it's 1,000 watt hours, which is 1 kilowatt hour. As we know, 1 kilowatt hour is 3,412 BTUs. So 1 kilowatt of lights will provide 3,412 BTUs of heat over the course of 1 hour. And that's whenever you design a building and design a heating and cooling system, you have to take that into consideration. We know how heat is measured, so this is very much a review. We know BTU is the amount of heat required to heat up 1 pound of water 1 degree Fahrenheit. That's something you should know. We know that furnaces are rated in BTUs per hour. It's a little subtlety, but the furnace rating, if it says 100,000 BTU per hour furnace, that actually means that's the input. The output depends on the efficiency. A cooling system is the opposite. So if you have a 36,000, which would be a 3-ton system, a 36,000 BTU per hour cooling system, that means it can remove 36,000 BTUs per hour. Okay, so that's how heating and cooling is rated. Again, this is a review, so we know that sensible heat is when heat is transferred and there's a change in temperature. We know that latent heat is when heat is transferred and there's a change in phase but no change in temperature. They say change in moisture content. I don't really like the way they say that. They're thinking about humidity in the air. But the kind of important thing that we haven't gone over a whole lot but was mentioned is enthalpy. So the total heat flow, or the total heat in air, is based on the sensible and latent heat. So if you have, if you remember on a psychrometric chart, enthalpy was next to dew point on the left-hand side. That tells you the heat in the air, both in terms of sensible, so the dry bulb temperature, but also the latent heat and the moisture in the air. So if you can have, 70-degree air that has very low humidity, and then you add some humidity to it without increasing the temperature, so it's still 70-degree dry bulb, but there's more vapor in it, it's going to have more latent heat, which means it's going to have a higher enthalpy. And that's something that you have to consider, both in terms of your heating and cooling systems, but also in terms of building comfort. And we know that buildings can lose heat to the environment in other ways, right? So we have airflow, we have heat through the building surfaces, and then we have solar heat gain. We've also discussed the principle of thermal mass. You should remember from our passive solar lesson, right? So we know that different objects can store different amounts of heat. And we know that concrete is a good thermal mass, which means it can absorb heat, more heat than something like a carpet or a ceramic tile or something that wood that's not a good thermal mass, right? So we know that things can store more heat. And there's actually a table that's posted in this week's lesson that give you the different specific heats of different substances. And this is really what this is all boiling down to. And that is, how do we use this knowledge to our advantage when we want to keep our buildings at a comfortable temperature and comfortable humidity. So I'm going to go over this in a separate presentation in a little more detail, but this is all a review. So we know that the R value is the resistance, right? And so that higher resistance means a higher resistance to heat flow. So you can add R values together. So higher R is better. And then we know that U is the inverse of R, so 1 over R. And that a lower U is better. And U is transmittance. Okay, U is actually transmittance. Ignore the conductance part, it's transmittance. And so we want a low U value. Again, this is a review, because the U is transmittance. So we want to transmit less heat. We want to prevent heat flow. And so a low U is good, a high R is good. Okay, so more insulation means a higher R and a lower U. And we know that they're the inverse of each other. Now there are standards for R values and U values in buildings. So the International Energy Conservation Code is this is a code that is propagated by this international body, and basically what it is the sort of best practices for efficient buildings. So insulation levels and air sealing and water vapor barriers and things like that. And so they publish this code, and they just put it out there. And what the intent is that you can adopt as whatever code you want. So basically, if I'm the city of Wilmington, and I'm like, I want to update my building codes, instead of having to come up with my own code all the time, I can just go to the IECC, adopt as much of their code as I want. But the intent of the IECC is to just sort of make it easy for people to A, know what the best practices are in terms of energy efficiency, and B, just make it easy to figure out what code to use. We're not going to really dig into a whole lot of detail to the IECC, but I will show you a little snippet here, because this is posted in this week's lesson. Okay, so this is what was posted. This is freely available. This is the IECC. Or no, this is the IRC. This is the International Residential Code. So this is basically your building code. Same principle, but it's International Residential Code, so it's just for residential buildings. So this covers everything, right? So we have planning, foundation, floors, walls, wall covering, roofs, assembly, chimneys, and here's the energy efficiency part, which you can use the IECC. Repairs, all this stuff. So again, this is all put out there. Duct systems, chimneys, all this. Plumbing, everything. So we'll look at this a little bit more, the International Residential Code. And again, the idea here is that to sort of make it easier for people to figure out, what to make their codes by providing this as sort of we'll say a suggestion that they can take as much as they want out of. Okay, so I'm not going to go over this example. I'm going to go over a separate example in a different presentation. But basically, when you do a heat loss calculation, what you want to do is you take all these you find the R values of these surfaces, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 surfaces here, and remember, you can add the R values of these. So that's what you'll do in the lab. You're going to add the R values of these different surfaces, and then you invert it to get the U value. And then you can calculate the heat loss, right? Then we have our heat loss equations, right? Our UA delta T, and the seasonal heat loss, which is, again, I'll go over in a subsequent presentation, and that's UA times HDD times 24. Okay, so the idea is when you really do a building heating load, you want to figure out how much heat am I going to lose through these surfaces throughout the course of the year, or, well, there's sort of two aspects to it. One is how much heat am I going to need to add to the building to keep it warm the entire heating season, and how to keep it cool throughout the cooling season. So in order to do that, you need to figure out, the U value of all the different surfaces, the walls and the ceiling and the foundation and so forth, and then figure out, okay, in a typical year, how much heat am I gonna is going to go through that, and then that's how much heat you have to replace over the course of the year. And then, of course, for cooling, same thing, how much heat am I going to gain, and then that tells you how much cooling you're going to need. But we can also use this to design our system, the size of our system. So this is something we really haven't gone over, but we will use a little bit of this in your lab this week. So I want to go over how this table works. So your design temperature tells you, it's based on the climate, okay? And you can see we have a percentage here, and then we have a design. This is a dry bulb value, okay, so outdoor air temperature. So what these numbers mean are, this percent, it tells you how that the climate throughout the entire year, okay, so day and night, 24/7, 365, is warmer than this temperature, okay, warmer than this temperature, this percent of the time. Okay, so what this is saying is, wherever we are here, and it doesn't tell us where, that it is warmer than 89 degrees outside 1% of the time. So that's right, so 24/7, 365. So we'll say 1% of the hours of the year it's warmer than 89. And the 99%, it's actually the same it's the same nomenclature. It's warmer than 3 degrees 99% of the time, which another way to think of that is it's colder than 3 degrees 1% of the time. Okay, so again, this is warmer than this temperature this percent of the year. So this basically tells you almost the really, really hottest part of the year, it's 89 degrees. Like, it gets a little hotter than that on average, but very, 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 very infrequently. And it very, very, very rarely gets colder than 3 degrees. Okay, so why do we care? If you think about designing your HVAC system, okay, so you have a house, and you're trying to figure out, like, how much heat do I need, right? How big is my system? Do I need, whatever, 100,000 BTU? Do I need 80,000 BTUs per hour? Whatever. And in order to do that, you need to know your design temperature. And what you do is you think at this point, okay, so if it's 89 degrees outside, and you usually use a base temperature of 65, okay, and you say, okay, this is like just about the hottest part of the year, and I need to cool it down to about 65. And you take all the stuff that we've done, the R values and the U values of all the surfaces, and you say, okay, when it's that hot outside, how much heat is going to come in through the surfaces? And then you also take into consideration air leakage and so forth as well. And then you say, okay, well, that's what my cooling system has to be able to remove that much heat over the course of 1 hour. All right, so let's say at that temperature you're going to, it's like 60,000 BTUs of heat are going to be coming in to the building. Then you need a cooling system that can remove 60,000 BTUs per hour, right? Which is, again, that's our BTU rating, if you remember from a previous slide. And the same principle for the heating. So you say, okay, this is almost the coldest it's ever going to get. How big does my heating system need to be at that point? And you can see the delta is going to be huge, right? So at 65 degrees, we need to go from 3 to 65. So that's a big difference, right? So 62 degrees. Whereas this is, 65 to 89 is like 25 degrees. So usually your heating system in this area, in the Mid-Atlantic, we need to have a higher BTU rating for our heating system than our cooling system, because the delta is huge. It's a really big temperature difference when it's really cold. And the reason you do 99% and 1% instead of like the 100% is there might be a couple hours over the course of the year where your heating system like just can't quite keep up, but it's if you design it so it will be able to heat at the absolute coldest possible temperature, then your system's going to be too big most of the year, and it's going to cycle on and off, and it's just going to wear out, and you're going to spend more money than you need to, and it's a lot of wear and tear on the system. The same thing for the cooling system. You don't want it to be oversized. So you kind of find that sweet spot where it's just, it might get a little too hot, it might get a little too cold, but you'll be all right the rest of the year. And that's how you use your design temperature, right? And so you will use that, as I said, in your lab today as a little bit of an addendum. So, okay, so hopefully that gives you some insight into this week's content and this week's lab.